Okay, so next up is set theory. Getting into some modern mathematics a little. So set theory was developed roughly 1850 to 1930. Obviously, people have been thinking for a long time, so there were some inklings of it beforehand and some developments afterwards. But pretty much the theory was developed the later half of the 19th century, first part of the 20th century. Kind of the big culmination, the heyday of it would have been around the time of World War I, the 19 teens, around the time Julia sets were being developed, which the power in those wasn't really known until 65, 70 years later when Mandelbrot was doing his work and really showed how powerful the Julia sets could be. But he was doing that was figured out on a computer. It was definitely something that was not figured out by hand. The basic idea of set theory is the math you're probably used to working with is we work with one number at a time, right? Each number is an individual thing, and when we add stuff and subtract stuff, we look at the properties of that particular number. Set theory is where we're going to work with collections of numbers. We're going to group similar things together and work with the collection instead of individual things. So I assume everybody's probably familiar with what's in my hand here, a regular deck of cards. So this is the example I was thinking we could go through and show why we want to learn set theory for programming. So let's say we have a card here, right? Just shuffle them, pick one at random. So I got the 5 of hearts, right? So 5 of hearts. And that's how we identify the card. I hope everybody's familiar with the rules of poker because that's what I'm going to use here. If not, maybe pause the video and check the rules of poker. But say we're writing a poker game. We want to set some rules up. If we dealt with it one number at a time, what sort of rules do we need? Well, 5 is bigger than a 4, bigger than a 3, bigger than a 2, bigger. So we need the high card rule. We'll have to write up a rule for a high card. So like 5's bigger than 4, 5's bigger than 3, 5's bigger than 2, ace is bigger than the 5. We move our 1 up to the end. But that's just one rule. We have to do 3 different things just for this one card. Then we need a pair, right? Which means we have to check the other cards. And if we have this card, we also have 5 of diamonds, 5 of clubs, and a 5 of spades. That one's kind of hard to draw. Something like that. But another rule for that. And then that continues, right? We need to check all the other cards we have to see if they're hearts, to tell if we have a flush. We need to check all the other cards we have to see if 5 fits in as a straight. Have to check all the other cards to see if the 5 of hearts fits in as a straight flush. And there's lots and lots of things we have to check. But like the way I wrote out the names of these cards, we already kind of have a way of splitting that up, right? We know what that card means because it has a rank and a suit. So we could do a lot more if we look at it as a collection instead of an individual one that we have to write a bunch of rules for. Obviously, it would take this whole board just to make a rudimentary list of the rules we need, not even begin to write them out. But if we think about it as, instead of looking at each individual card and look at collections of cards, then we can write a lot less rules. So let's look at that example real quick. Let's formalize what I was just writing up there a little bit more rigidly, like we what we're actually going to do when we write a program. So you might remember back in week 2 we did all that numerical stuff to represent things. So we need some sort of number to represent our card, and we're going to use this either way. So let's say a 0 is our ace of hearts. That'll make it easy. There's reason when we ask for something, we ask for the beginning and we count from the end. So our first thing is a 0. So there's a slight discrepancy of when we ask for something and when we count it. We'll talk about that soon. We start with 0. This is a short way to put it. Then our first card number 1 would be the 2 of hearts. Card number 2, the 3 of hearts, and just kind of go on like that. So the 5 of hearts is going to be number 4. And we'll just start with hearts and then do clubs and diamonds and then spades. And just put them in order like that. Somehow that last little picture didn't work. So the card number 51 would be the king of spades. The very last one there. And actually there's a slight modification we could make here. Just like A seems like it should be a 1, right? We'll modify that when we get to the break it up into sets. And line that up a little bit better because 1 doesn't line up with any of the 1 cards. 2 doesn't line up with any of the 2 cards. So that's kind of an issue that's going to make the code look confusing right off the bat. So we'll kind of adjust that here in a moment. But let's say we assign number 4 to the 5 of hearts. And then there's 13 ranks in each suit. So the next 5 comes up 4 plus 13 is 17. So 17 would be down here. 17 would be the 5 of clubs. Another 13 would be 30 to the 5 of diamonds and 43 to the 5 of spades. So then when we go and write rules for if we have a pair, 3 of a kind or 4 of a kind, those are all kind of the same. We have to check and see if we know we have card number 4, that's the one that was randomly selected. Do we also have card 17? Have card 30? Have card 43? And we have to check each one of those things to determine if we have a pair, a 3 of a kind, 4 of a kind. And then our other things, the high card. There's a lot to check there. Just on a low number like a 5 is the 2 of hearts up to the 4 of hearts, so that's numbers 1, 2, and 3. So we have to check and see if our card, which we know is number 4, is that bigger than a 4, or bigger than a 3, bigger than a 2, bigger than a 1. But then we have the other suits, right? Because if we're just looking at high cards, the 5 of hearts is higher than the 3 of clubs as well. So we also need these plus 13. So bigger than a 16, bigger than a 15, and bigger than 14. And then 13 after that. Bigger than a 29, bigger than a 28, bigger than 27. So we have to specifically write rules to check every one of those just to see if our card fits the high card. And then we have to do all that for every rule of poker. And you can see it's going to get very long, very complicated very quickly. Alternatively, we could split it up. We could apply set theory. Split it up into collections, and then we write our rules for the properties of the collections. And we already have a collection just in the way we identify that card. So we have 13 ranks and 4 suits, and there's 52 cards, right? So if we divide that up, a total of 52 divided by 13 would give us the 4 cards. But, like I was saying a minute ago, we start numbering at 0. So let's back that off and say 51. 0 to 51 is going to be our 52 cards. If we divide that by 13, whatever number, something in between 0 and 51, if we divide by 13, we're going to have a quotient and a remainder, right? It's going to go as high as 3 with a remainder of 12, which fits nicely in here. Because then our quotient could be 0, 1, 2, or 3. There's 4 of those. And we have 4 suits. Or our remainders could be 0 through 12. 0 through 12 is 13 values, and we need 13 values for the rank. So that very quickly divides these 52 cards up into rank and suit sets. And then we can write the rules for our collection. Like anything in the rank number 5 rank, anything in the same rank as the 5 is bigger than anything in the same rank as the 3. And I said there would be a slight modification. If we do this, instead of starting with an ace, if we make our king 0, then everything else will line up nicely. Which kind of works if we go 1 to 52 and then divide by 13. Our last king would be a remainder of 0. But if king is 0, then ace becomes 1, 2 becomes 2, 3 becomes 3, and so on. So the numbers line up a lot nicer that way. It makes the code look a lot better right off the bat. And we just move the king back to, say, if the remainder is 0, then we have a king. So just a slight adjustment makes the code look better. But then we can use these collections, the properties about that number. And we can do them separately. Like for our high card, we don't have to worry about every single case. We don't have to check every suit. We just have to check the collection of 5s against the collection of 3s. Or the collection of 2s. Or whatever is involved. But we can write a whole lot less rules. To check for a flush, we just have to see if all of our cards are in this suit. For a rank, we just need to check a couple of the rank sets in order. Do we have like a 4, 5, 6, 7, and then 8? I guess I need 5 cards for poker. But we can write our rules for the entire set instead of individual rules for every card. Because remember, this is just one card. We then have to do that for the 6 of hearts, the 7 of hearts, the 8 of hearts, the 9 of hearts, and all the way through that huge deck. Have to write rules for every single one. But if we just list them 0 through 51, choose a random number between 0 and 51, call that a card, divide it by 13, then our quotient, which is a number somewhere between 0 and 3, will define what suit we're in. And our remainder, a number somewhere between 0 and 12, will tell us what rank we're in. And then we can write a much smaller set of rules. And not only is it smaller, it's more the way humans think when we deal with cards. Right? Because when we're looking at a hand of cards, we're thinking about these things, and our rules are based off this, not off this individual card. We don't think through every single individual card. So writing a computer program this way is going to be more natural to us, as well as a lot shorter. So that's kind of the example of I like to use for a really useful place that is easy to visualize. A really useful place the set theory is going to apply. So now that we've seen a useful place for it, let's talk about the math part of it. Let's talk about set theory. Okay, and to do that, before we get too far away from that example, is an example of that modulus operator we saw that we probably haven't used as much before. So to get our quotient, in Raptor, we don't have integer division, so we just floor whatever number we get when we divide. We divide to get the decimal, and then we'll floor it. So we'll take whatever our card is and divide by 13. And then that'll give us the quotient, or what suited it is in. And then if we take the card modulus 13, that'll give us the rank of it. I meant to put that in the example and kind of forgot to. And then when I realized I forgot to, I spilled coffee in a different spot on my shirt than I spilled before the last thing. And it's laundry day, and I've run myself out of t-shirts. And it's the middle of August. Way too hot to put on a long sleeve shirt. Sorry about that. I'll make sure something like that doesn't happen again. But that's an example of that modulus operator where we saw that we probably haven't used much. And everybody's going to see set theory. We're just introducing it here, so this is going to go kind of quickly. Really just the notation is all we're going to look at here. And everybody's going to see it later and to a different level, to a different amount of it, depending on where you're heading. So that example I threw up, I normally teach software development courses, so those are the first examples that pop in my mind. But cybersecurity people are going to use that as well. Whatever you're securing, you can set up rules for that collection, the collection of what should be there. And then trigger alarms when something doesn't fit the rules of the collection that you're securing. The set, the rules for that set. I was at a Cisco conference a couple years ago, and the speaker kind of referred to it like standing by an assembly line in a factory. If you're standing there by the conveyor belt watching toasters go past, and suddenly a refrigerator goes past, you know something's out of the order, out of the ordinary. So set theory, everybody's going to use it to some extent. So a lot of the details that you'll need will be worked in later IT classes, particular to your field. So just some notation. For a set itself, we're going to indicate that by curly braces. And we separate things by commas. So like, standard math notation is we would write this with a capital letter. I started writing an X and started to distinguish capital and lowercase, so I'll add some serifs on the X for a capital to make sure that stands out as capital. So the set X contains a whole bunch of little x's. X1, X2, X3, and so on. And we just put a comma separated list in between some curly braces. A very important set is going to be the null set. That's the set with nothing in it. And indicate that with this symbol, which is very, very important in programming, because that is, if you try to do something with a null value, a null set, the computer cannot handle that. The computer cannot handle that on its own. So eventually, if those who are going to do more programming stuff beyond this class, you'll get used to just get in the habit of checking to make sure whatever you're working with is not null. As far as us in this class, the people that put Raptor together, that was designed for a learning tool. So they already set it so that if Raptor encounters a null value, it puts a 0 in there. So it's handled in Raptor for us. But if you continue on, it's often not going to be handled. So that's kind of our main notation, our symbol for the null set, the nothing, emptiness, less than 0. We don't even have a 0 included in the set. It's complete emptiness, and computers cannot handle that. So it's important to keep track of. And our standard notation, just curly braces and the values in the set. So I'm going to use sort of an example to kind of walk through the rest of this. So let's make up a set with some numbers that we can work with. I'm going to write a curly U, and this will just be the universe of numbers we're looking at. And this is one of the core concepts of set theory. There's an awful lot of numbers, right? It'd be a whole lot easier to do our math if there weren't so many numbers, if we had fewer numbers to work with. So let's just put a few here. Something we can count on our fingers, the numbers 1 through 5. 1, 2, 3, 4, 5. So instead of working with an infinite number of numbers, we can just, everything we're going to do can be done with 5 numbers, and then we can do the math with that smaller set, just a handful of numbers to work with. And it makes things easier because then there's a lot less to deal with. It's one of the core things of it, but we're just kind of introducing stuff. So we have this set. This is like all the numbers we're going to work with. That's our universe. And I'll put a couple subsets in there. So the first set we'll call A. Let's do odd numbers in A. 1, 3, and 5. So, and then a set B. For set B, I will just include the number 4. Just one number in there. To indicate it doesn't have to be a bunch of things. A set can be a single value. So then, well, our number 2 is not included in there. We'll talk about that in a moment. So then we can do things with this by looking at the combinations of the sets. And a good way to introduce that with and talk about it is with a Venn diagram so we can point at it. You may have seen Venn diagrams before. That's where we have a rectangle with several bubbles inside and they kind of overlap. Actually, I want something to overlap here, so I'm going to add 5 to set B as well. Sorry, I'm kind of making this up as I go along, but have 2 numbers, but we could have 1 number in the set. I just wanted to make sure there's something overlapping. So set A is our odd numbers. So let's make this one our set A. So we have a 1, a 3, and a 5. And over here in this bubble, that'll be set B, which has a 5 and a 4 in it. And, well, all of our entire universe of numbers also have a 2 in it, so that's out here outside of everything. So a Venn diagram is just a common way to represent sets. So you may have seen that before, in which case you've seen some set theory, and probably just didn't know that's exactly what you were working with. So there's several things we could do with these, such as what's not in A. Our term for that's going to be the complement of A. And a couple standard notations for that are either going to be an A with a bar over it, or an A with a little superscript C. I can't remember which one the homework uses. I think your homework uses this one. But that's the complement. Everything that is not in A. So our set, the A complement, so it's A is 1, 3, and 5. So the complement of A is what's not in there. So 2 and 4 are not in A. And there we can kind of see how we could set up rules based off properties. Check the properties for odd numbers, and then if all set A has all the properties of odd numbers, and the complement of A is all the even numbers. So I guess we could also do the complement of B. I think this is the notation the homework uses. So B is 4 and 5, which means the complement of B, what's not in B, would be 1, 2, and 3. And then we have combinations of them, right? So, well, like on the Venn diagram, while I'm still talking about complements, like everything out here is in the complement of A. And everything in B that is not part of the overlap is in the complement of A. So we can do combinations of them. And there are two main combinations we can take. The intersection or the union. And more commonly used terms to help us keep track of that is an intersection is like and. It's inclusive. We have to have both of them. And a union is like or, as long as it's in one or the other. So where A intersects B, that's and. So only values that are in A and in B both. It's inclusive. It has to be in both of these sets. So 1's in A but not in B. 3's in A but not in B. 4's in B but not in A. So the only thing they have in common, the only inclusive part, is 5. So the intersection of them would be a 5. And the union, a union with B, is more like an or situation. If it's in either one. If anything that's included in set A, along with anything that's included in set B, and we don't need any duplicates. So set A has 1, 3, and 5. 1, 3, 5. Set B has 4 and 5, but we already have 5 included, so we don't need any duplicates. So intersection is what they have in common, and union is the entire joining both collections together without listing any duplicates. So a couple things left. I'll put it over here. First off, I said the word. A is just a piece of our U, our set U here. So A is a subset of U. And we mark that in one of two ways. This sort of curly thing like this. So A is a subset of U. Or it might have a line under it. And that just refers to what's going to be called a proper subset. Without the line, that means A can't be all of U. It's kind of like with our regular numbers that we're used to, the less than versus less than or equal to. Is usually we just use this one and just say subset. So like A is included in U, and if there's little lines here, that means A could be all of U. We could have just gave that entire set a different name. Kind of like the or equal to part when we just compare numbers. Is what I always relate it to. So we usually just use this. So A is a subset of U. And B is a subset of U. And obviously all of these, right? The complement of A is also going to be a subset of U. The intersection of A and B is also going to be a subset of U. So it's a smaller piece of our set. Possibly a smaller piece of our set because we could just give our entire set a different label. And that would also be a subset. And the last thing we're going to look at is one of our operations, a very important one is going to be the difference operation, or subtraction. I believe the homework uses this notation. We might use it, you might see just a regular minus, but typically that's not used for the homework. And when I checked, I think it had the notation I liked. I should have looked right before making this video instead of like 2 months ago. But, well, I should put some labels here. Okay. I want to take good notes. So this is subset. And then we also have, that piece of junk was too small to write with. Let's grab a slightly bigger one. The difference of sets, which is like subtraction, basically. So A minus B, or we might notate it as A slash B. The difference between the two sets. And what this is going to be, what it really means is A, the set A, except the intersection of A and B. Because if we put in some numbers here, A is 1, 3, and 5. And we want to take away set B. So set B has a 5, so we can take that 5 away, which is our intersection. But set G also has a 4, but there's no 4 to take away. So we can only take away the intersection. And that's the difference of sets. So that is kind of the starting point we'll need. We have some, excuse me, we have some set that includes these numbers and subsets of sets, and we can have subsets of subsets that can continue on. Our null set, keep that in mind. The nothing thing. Then the complement of the set is everything that's not in the set. So like the complement of A is everything that's not in A. So here, A's are odd numbers, which means the complement of A is the even numbers. Intersection is what they have in common, where, it's like where they intersect, the common point between them. The union is just joining everything together. I'm trying to think of a word that doesn't refer to union, and nothing's coming to mind. So like a labor union, right? All the people that work in the factory coming together, joining together and putting aside their differences and focusing on what they have in common to get what's best for each one of them. Union, or like the historical usage, in the Civil War, the Union of the states, all the states came together, joined together. So that the union is all of them joined together, and we don't need to repeat things, so we don't need duplicates. And then the difference of a set is kind of like subtraction, but we can't subtract unless it's in both sets. So we're taking away the intersection. And that's kind of the basic starting point for what we'll need for set theory. And so that's a quick introduction to set theory, really introduction to the notation in set theory. And most of us are going to use set theory to varying extents in whatever field of IT we go into. So in future classes, you'll learn more about how to use set theory particular to the field you're heading into. So just kind of introducing the notation here mostly. But one thing we all will be doing with it is we can answer some questions. We can use just the basics here to answer questions. In particular, answer yes and no questions, right? Like in the example here, is 5 in our intersection? So yeah. Is 1 in our intersection? Nope. So false for that. True, false, yes, no. There's different ways we can phrase a binary states. And that'll be important here in a few minutes when we're talking about our selection structure for writing code, for coding up a program. There's different ways we can phrase binary states, and we'll want to change back and forth between those different phrasings to find the one that fits that situation the best. But we'll talk about that here in a few minutes. Yes and no, or true and false, are going to be our basic ones. Often when we're thinking about it, yes and no, because that's what we would use in common communication, right? We don't usually say true or false a whole lot when we're talking. It doesn't show up in normal communication. I mean, if somebody asks, are you ready for dinner? We don't say true. We say yes. So often that's a better way to think of it, but at the same time, there are places where true, it would be a better way to think of it than yes. We'll talk about that in more detail. So we can answer yes and no questions. Is 2 in A? It's not. And that's important. That's another way we could phrase that question. Is 2 not in A? 2 not in A. So not in A is the complement. And then we have these fancy words, math terms, intersection and union, but I went ahead and wrote out some more common usage, and or. And so we can answer yes or no questions with those things in mind, not, and or. And that's what lead into the next one we're going to introduce, Boolean Algebra. Just a quick introduction on that, and that's one we all will use. So set theory with yes or no questions, true or false, which connects it back to that stuff earlier about logic, those truth value testing the truth value of something, when we can ask true or false questions of our math based off intersections, unions, and complements, or, and not, as we would more commonly say that.